Hi, in this video, we want to take a look at maximum likelihood estimation. Okay, so we're in the situation that I have data, I have a theorized probability distribution for my data, and I'm pretty confident that I've got the right distribution. And what I want to do, I want to use my data to estimate the parameters of that probability distribution function. Okay, typical thing that we do in statistics is called point estimation. Now, one way I can go about this is that I could connect population average to sample average, population variance to sample variance, and population skewness to sample skewness and stuff like that. I could go through that process and that would work out. That would give me a system of equations, and that is very similar to what we call method of moments. All right, so now method of moments, that's very natural, very intuitive, but there's some downsides. Some downsides are like, well, we don't always actually get the best estimate possible, and it's possible to get absurd values that don't work out. So we want another approach. We want another way to tackle this. So I want to estimate these parameters using my data, and I'm going to use math, of course. Well, if you've taken calculus, let's say Calc 1, business calculus, anything like that, you remember that you had to do optimization problems. Do you remember that you had to take find the maximum or minimum of different functions? Well, what we're going to do exactly that. We're going to find the maximum, but here's the difference. Here's where things get interesting. I'm going to take my probability distribution function. Normally, the variables, the data is the variables, and the parameters are the constants. What I'm going to do, I'm going to take the same equation, I'm going to switch it up. I'm going to make it so that the observed data, the variables, are the constants, and the parameters are the variables. And then I'm going to go through and do that maximization process, that optimization problem from business calculus, from Calc 1, and whatever gives me the maximum is going to be my parameter estimates. And this is what we call maximum likelihood estimation. So I convert the density, the probability distribution function to a likelihood, then I find the maximum on that. And so likelihood, maximum, that's maximum likelihood estimation. Okay, so some features about this. Maximum likelihood frequently gives us minimum variance and unbiased estimating, especially when we have large sample sizes. That's very attractive. Another aspect is that we will always get a plausible value for my parameter estimates. So method of moments fails in this aspect in some weird cases, usually with small data. It's usually not an issue if I've got big data, but it's still a nice aspect that I know if I'm going to go through the process of doing this, I'm going to get something that I could potentially use. Okay, so now let's connect probability distribution functions and likelihoods. This equation right here, it doesn't really highlight very well on this, but if I look here, this is my equation. This is really the core of maximum likelihood estimation, is this equation. Over here on the left is the probability distribution function for the entire data set. Now you'll notice that each observation is treated as a variable in this situation because it's multivariate, because I have multiple values I'm working with. And here are my parameters floating around over here. And I picked mu and sigma squared just because those are typical for a lot of situations. But any parameters for the distribution function go right here. Now, I'm in a situation that I have data in my hand. I'm holding it. I've got it. I want to use my data. Okay, so if you think about it, the variables are no longer variables because the data connects to variables. The data is a constant value because I know what it is. It's not changing. It doesn't vary. Therefore, it's not a variable. So what I'm going to do, I'm going to treat my data as constants over here. I don't know what my parameters are, so I'm going to treat the parameters are the variables. So I've just switched the roles of the data and the parameters, and what I'm going to do? I'm going to call this the likelihood function. So the equation is as the same, but the components, the things that go in, the inputs have different roles. Okay, so when I talk about a probability distribution function, the data is treated as the variables and the parameters are the constants. When I talk about likelihoods, the parameters are the variables and the data are constants because I know what those are. I have them in my hand. Okay, so now what are the steps in this process? Okay, so typically what we're going to do when we're learning this material, this is going to be a pencil and paper exercise. And anytime I'm in a situation where I have a probability distribution that isn't like well established, isn't well known, I'll have to go through the pencil and paper method. I can look in a textbook, I can look on Wikipedia, and I can find maximum likelihood estimates for a lot of things and shortcut this and just jump to grabbing that. But anytime I'm in a new situation, I have to go through and do it by hand, pencil and paper style. Now, first thing we're going to do, we're going to take the probability distribution function. We're going to plug in our observed data. Those are the constants. Then I'm going to treat this object I have on paper as a function on the parameters. And then I'm going to maximize that function. Now, typically, in most of the times, if you're taking a theory course, you're going to go through and you're going to use calculus to do this. We're not going to do that. We're going to let R do all the heavy lifting for us. We're going to be lazy, and I'm just going to plug it into R, get the value, boom, I'm going to be done with it. I'm not going to worry about taking derivatives or any junk like that. Now, another very nice property of maximum likelihood estimation. Let's say I'm in a situation that I don't really care about the parameter. I care about a function on the parameter. So I'm interested in G of the parameter. I'm interested in the function value. I really don't care so much about the parameter itself. Okay, well, if G is 1-to-1 and I have my maximum likelihood estimate of theta, what I can do, I just plug it in and that gives me the maximum likelihood estimate of G of theta. So the maximum likelihood estimate of G of theta is G of the maximum likelihood estimate of theta. This is very nice. This doesn't work out as well in terms of the method of moments. All right, so that nice connection works out very well for us. And this works out anytime that G is 1-to-1. All right, so let's run through an example, but I'm not going to do any calculus at all. I could, maybe I should, but I'm going to go through and I'm going to work through this pencil and paper style. When I get to a certain point, when I get to the maximization step, I'm going to go through, I'm going to plug it into R. I'm going to let R do the heavy lifting. Okay, so let's say that I have data, independent, identically distributed from a Poisson random variable. All right, so I have my data. I want to know what is the parameter of the Poisson random variable. I want to estimate lambda. All right, so here's my data. I've got, what, about 10 data points, something like that. All right, so I'm going to go through and I'm going to work through this and I'm going to get my likelihood function. And I'm going to try and simplify things down algebraically to make things easy in the upcoming steps. So here is the distribution of the entire data set. So all 10 points given lambda. All right, well, I have independence between my data points. Therefore, I can factor among each of these. So here, f of all the data is f of the individual data multiplied together. Okay, so once I have this going on, I've got everything factored apart. I'm going to go through and I replace f with f. I just go in and I plug in the actual data point. I plug in the data point. I plug in the data point. I do this repeatedly. Okay. So now on this step, I see that I have lambda to the power of something, lambda to the power of something, lambda to the power of something, and I'm going to multiply those all together. Well, if I keep on multiplying a bunch of things together and I have the same base every time, it's all about that base, then it's going to be the base to the power of the summation, right? You remember that from college algebra? So all of the lambdas together, when I do my multiplication, give me lambda to the power of the sum. I just add up all the exponents. Easy peasy lemon squeezy. All right, so now I see that I've got e to the negative lambda. I have e to the negative lambda. I have e to the negative lambda over and over and over. I'm multiplying them together. Well, when I have the same base, multiplication is just summation of the exponents. So I know that I have e to the power of negative n lambda. Okay. And now here on the bottom, I see I have a factorial, I have a factorial, I have a factorial all the way across. I'm just going to multiply those all the way through. Okay. And so now, just to make this a little bit easier to work with, I know that a summation is equal to n times the sample average. So I replace the summation with n times the sample average just to make it a little bit more compact. And also, you'll notice that up top in the numerator, all I have is x bar. I don't have individual x's, so things are a little bit simpler. All right, so now I know that this expression is equal to my likelihood function, just that I'm treating lambda as the variable, and I'm treating the observed data as constants. Okay, so now I'm going to rewrite it in this funny manner with this fraction here. And I have lambda to the n x bar, e to the negative n lambda. Okay, so when I look at this, my goal is to maximize the likelihood in terms of lambda. So I have something that does not have anything to do with lambda. I have a lambda part and I have a lambda part. This part right here, in terms of lambda, is a constant. So I honestly, I don't even need to pay attention to this. If I maximize just this part over here, the part that's highlighted, if I maximize the part that involves the lambda, I also maximize L at the same time. So what I can do, I can just go, well, L, my likelihood is proportional to this. I'm only going to work with this part. I'm going to ignore this constant because the maximum is going to be the same either way. And this is just a little bit cumbersome for me to work with mathematically. Okay, so phone call. It was a spam call. All right, so let's go ahead and actually do this. So what I need to do, I need to find lambda that maximizes this expression. Okay, so what I'm going to do, I'm going to take my data and I'm going to find the sample average. I call it x bar, and n is equal to the number of data points I have. So I'm using the length function to get that. And here, so I'm not actually going to do any calculus. I'm going to just compute things. And I'm going to let R do the computations, and I'm going to use what R spits out to tell me what is the maximum. Okay, so I'm going to take a bunch of potential lambda values. I'm going to go from, so here I have to just kind of guess what's reasonable. So I have to go from a low value that I think is plausible. So I know that lambda has to be greater than 0. So I start with, I'm just going to start with 1. I'm going to go up to 10 just because that seems reasonable. The data is going from 4 to 8. So yeah, seems okay. And so now what I'm going to do, I'm going to plug in all of these different, so this is a vector of different lambda values. I'm going to plug in these lambda values into this expression and see what happens, see where I get the biggest one. So here, I'm just doing exactly that. I'm finding this expression on the actual lambda values. All right, so now once I've done that, what I want to do, I want to find where is my likelihood maximized. So L is proportional to the likelihood. I'm going to find the maximum L I can find, and I want to find the corresponding lambda. And so which dot max goes in, it finds the position of the maximum value, and it gives me that position. And I know that that position corresponds to the lambda I want. And so here we get a maximum likelihood of 5.8. All right. So now I want to go ahead, I'm going to plot all the lambda values. So here, this is the lambda value that I could look at. And this curve corresponds to the likelihood of that. Well, I can see to a little bit left of 6 is where I'm getting the maximum value. And that looks like it's about 5.8. All right. So that looks pretty good. And I can see I'm pretty confident that this is like the maximum likelihood estimate. And you'll notice I got this without doing any calculus at all. Now, if you were to go through and do the pencil and paper calculus and worked it out, you would find that the maximum likely estimate of lambda is actually x bar, which is 5.8. Hey, isn't that what we got? So it was a little bit off. My estimate was a little bit off when I did the computation route, but it's pretty close. If the more values I have in lambda, and the more close the values are to each other in the vector, the better of an estimate I will get. But this is pretty darn close for the amount of work I put in. All right, so let's do another example. And once again, I'm not going to do calculus. Did you see any derivatives in that last one? No, you didn't. We don't need it. All right, so here, I'm going to mix it up. Let's say that I've got uniform data. I know the lower bound, but I don't know the upper bound. Huh. Okay, so I have data that is from a uniform distribution. I'm going to say the lower bound is 0, the upper bound is theta. I don't know theta. I want to know what theta is. I want to estimate it. Okay, so here's my data that I need to work with. Now, so I have a multivariate distribution, and I know that since we're dealing with independence between my observations, this just factors into a bunch of individual terms like that. Okay. Well, now what I'm going to do, I'm going to use the fact that I'm dealing with a uniform distribution. All the distribution is 1 over theta every single time. Okay, so I replace each of these with 1 over theta. Okay. Well, I see I'm multiplying the same thing by itself over and over and over. This is just 1 over n, or sorry, 1 over theta to the power of n. All right. So now I have my likelihood function. So the likelihood of theta given my data is 1 over theta to the n. Whoa, 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 whoa. Something's weird here. Something is strange. Something is unusual. The x's aren't in there, right? I look at this. I go, hey, where's my x1? Where's my x2? x3, x10. Where is it? It's there. It's just not very clear. Okay, so let's take a moment and remember that when I'm dealing with uniform distribution, x is always between the minimum value and the maximum value, right? Okay, so when I look at this, every single value of x is less than or equal to theta. All right, that tells me that 2 is less than or equal to theta. 3 is less than or equal to theta. 5 is less than or equal to theta. And 4 is less than or equal to theta. So if I think about that, well, 5 is less than or equal to theta. That gives me some information about it. So what I know that the maximum value of my data is less than or equal to the maximum parameter of the uniform distribution. Okay, so how do I incorporate this? What I'm going to do, I'm going to use this fact when I do my calculations like I did previously. So here, what I'm going to do, I'm going to take the maximum value of x, and I'm going to set that to be the beginning of my potential theta values. All right, so let's do that. So here's my data. Here is the number of data points I have, which is n, and the maximum I have. So here it's just going to be 5. I'm going through the process just to, so you can see how to work through. And so now I know the minimum possible value that I can get for my theta would be the maximum value from my data. So I'm going to make a sequence of potential theta values, and I'm going to set the minimum to the maximum of the data. And I'm going to go out to some value that seems reasonable, seems big enough that this isn't really an issue. So all of the data goes from 2 to 5. Okay, so I'm trying to find a number that is that I know will always be greater than the values in the data. 10 seems big enough. And I picked 1,000 as the length just because 1,000 seems like it's enough. All right, so L is equal to 1 divided by theta to the power of n. That's from my maximum likelihood calculation a moment ago. That's from up here. So this part here gives me my L when I plug in the theta. So now what I want to do, after I get my likelihoods, I find the maximum of them. All right, so the which.max function gives me the position of the largest likelihood. I grab that position, and then I grab the corresponding theta. Well, when I do that, I see that 5 is the corresponding theta. So this tells me that my maximum likelihood estimate is the maximum of my observed data. Huh. And so now let's plot it. So here, if I go through, if I plot all the theta, so theta values are along this axis, the likelihood is vertical, and I can see that the curve is just decreasing. And if you're familiar with college algebra, 1 over theta to the n, that will be a strictly decreasing function as theta increases. So I know that the maximum value I will get will be the endpoint of 5. So now I've got maximum likelihood estimate. And you know what? I didn't do any calculus. All right, well, that's all I've got for you. Take care and goodbye.